Okay. We derive the equation P equal to H rho G, right? We derive uh, P equal to rho G H. And how we derive it? We figure out that derivation of pressure, change of pressure dP by dx along x-axis is coming 0 and dP by dy along y-axis coming 0. But along vertical direction or z-axis, dP by dz equal to it is coming minus rho g. Minus rho g minus gamma, right? Okay. This equation, we derive it for incompressible flow. Incompressible mean rho constant, rho not changing. But what will be if its fluid is compressible? In that case, which equation will be used? That I put it over here. Okay. Though most of the time we'll talk about the incompressible flow, but in part B, Soshishar will teach you some compressible flow. Then you might need to apply some knowledge that what will be this equation if flow is compressible. Okay. So, so write this equation del P by dz. This rho is no more constant for compressible flow. And from ideal gas law, we know P equal to rho RT. So from here, we can figure out the rho, P by RT. This rho will put in this equation. So after rearrange, you get this one, dP by dz minus Gp by RT. Now this dz, you take out from there, bring it right here. And you see in this equation, this P will bring bottom of dP. So our equation will be, if we rearrange dP by P equal to minus G by R. Now on the right side, the derivative will be dz by t, this value. Now, if you make integration from 0.1 to 2, so G is constant. Universal R is universal gas constant, that is also constant. Then you derive that one 1 to 2. Okay. If you derive 1 to 2, right over here, you are getting ln P. So after you put the limit, ultimately becoming ln P1, P2 by P1, left hand side. And right side, they are keeping like that. G by R keeping front of the integration and dz by t. Why they put it like that? Because we are not sure if t is a function of z. In some case, temperature of the fluid might depend on the depth. So that's why keep it over here. But if for certain condition, for example, isothermal condition, T is constant, say T naught. In that case, you make the derivation, it coming like that. Because say this P1 we keeping in the bottom. Okay, this is ln P1 and minus G. If T is constant, then you will have G2 minus G1, right? Now, what is this one? EXP, exponent, e to the power this much, okay? If you have log x equal to A, what will be value of x? X equal to e to the power A, okay? So that's they did it over here. So you just have to figure out P2 by P1 will be e to the power right side. Then figure out the P2. Now in absolute pressure, what is the difference between gas pressure and absolute pressure? If you have the gas pressure, some type of reading from some media, or you are getting pressure inside a pipeline, inside a tank, that will give you the gas pressure. With that gas pressure, if you add atmospheric pressure with this gas pressure, then this mass pressure will be absolute pressure. And if your gas pressure is vacuum, then you put atmospheric pressure over here, then minus vacuum pressure. And gas pressure is always might be positive or negative, but absolute pressure excuse me, but absolute pressure will be always positive. Okay, you see this mass your atmospheric pressure. I'm sorry, not this mass. This was the gas pressure. Atmospheric pressure, this mass. That means if you think that this is your x-axis, then this is atmospheric pressure. And atmospheric pressure, this is absolute zero pressure. Okay. So if you have gas pressure is negative, gas pressure always you will get most of the time more than atmospheric pressure. But it is negative, then your atmospheric pressure line is this one. So gas pressure will be over here. If it's vacuum, that means negative pressure. Then this gas pressure, if we add absolute atmospheric pressure, you get this much pressure instead of vacuum. So just to remember, if you have a gas pressure, then you need to add atmospheric pressure to have absolute pressure. Okay, just this formula. Absolute pressure equal to gas pressure plus atmospheric pressure. And we already apply it in some problem, I think. Okay. Right over here, I just put some unit of pressure, kilopascal, megapascal, and also we use gigapascal, right? And what is the bar? Sometimes we call 1 bar, 2 bar. Bar mean 10 to the power 5 Pascal. And atmospheric pressure is close to 1 bar because atmospheric pressure is equal to 101,325 Pascal. So if you make it 10 to the power 5, it come 1.01 about. So the same, right? and atmospheric pressure 101.33 kilopascal. And it is better to remember this value because when we solve the problem, most of the time will not give you the value of the atmospheric pressure. So as a student of fluid mechanics, you need to remember some value, some parameter. For example, density of air, then density of water, and their viscosity. You need to remember that data. Then what is the atmospheric pressure? ATM, that one you need to know. Other thing you need to know, what is the standard room temperature? Okay, and density of that must will be enough. This one more thing you need to know. Widely we use mercury in the manometer. So what is the density of the mercury? Okay. Okay. Right over here, they showing that how you can get higher force from by applying a little force from the fluid by applying fluid law. So if you see right over here, inside the fluid pressure is P. So if fluid pressure is P, how much will be force over here? Say you apply force F1 through a piston right over here, then that force will go through distribute over here. So if due to the apply force F1 right over here, it create pressure P. So we know that F equal to P by A. So sorry, mistake, not F by A. P equal to F by A. So you are getting F equal to P into area, right? So if we apply force F1 and inside create pressure P, then we can say F1 equal to P into A1. And that pressure will be transmitted through right over here. And what will happen? If you try to push him down in the left side, what will be right side? Fluid will try to move upward, right? But you don't want to move the fluid upward. So if you try to keep him in the same level, you need to add some weight over here in the piston. So if you add some weight, that means you need to apply some force. So right over here, we can say P equal to F1 by A1. Similarly, but pressure inside the fluid is same. So right over here, we can say P equal to F2 divided by A2. Now this P is same, both sides. So I can write down F1 by A1. A1 equal to F2 by A2. Now you see we apply a small force F1. and we'll see what will be the magnitude of force on the right side. That we'll figure out. So from here, if you figure out the value of F2, then F2 equal to A2 divided by A1 into F1. Now you see ratio of A2 by A1 will be greater than 1, right? That means you are getting F2 will be always greater than F1. So what does it mean? If you apply more force, but in the other side, you are getting higher force, although fluid pressure remain the same. And this principle we can apply to get some mechanical advantage. Mechanical advantage mean applying little force, but you are getting higher force. What is the example? Like we use hydraulic jack, lift, hydraulic lift, then press, and all other hydraulic control, they use this mechanism. Okay. Mechanical force is applied through the jack action or compress air. This is one example. Say you are driving car, your tire getting bad, you need to change it. You just put the hydraulic jack or pneumatic jack, same thing. Hydraulic jack use fluid and pneumatic jack use air. But if you apply little force by your uh, foot or by hand, you be able to raise your car gradually due to this reason. Okay, next class we'll check in that if fluid pressure is same in all direction or not. That we'll check. For example, this is top surface of a lake. Now, inside that lake at a depth H, you have a very small fluid element. Say this one. So, how much will be pressure at that surface? It depends on how much the height, right? You can figure out P H P rho G, H rho G, right? P equal to. This will be vertical pressure, but how much will be pressure this side, and also from bottom? That means the Pascal is saying the pressure in all direction is same. If the body is not moving, if body remain in static condition. So that we'll figure out. That means if you, in that case, Px equal to Py equal to Pz. That means all three axes, the pressure value will be same. If this fluid element is not moving along vertical axis, then pressure will be changed, otherwise remain the constant. So let's derive it, how we can derive. We consider a infinitesimal small wedge-shaped fluid element. Infinitesimal means very small. Wedge-shape means you have a brick, you take half of the brick. It remain at rest inside a fluid. So if it is very small, still it has a density, it has a weight, right? And dimension is non-zero. Still it has some dimension. So we are thinking this is 3-axis, and the vertical axis, this height from here to here is dz, this one. And this is x-axis, so this length is d delta x, or this one. So this is delta x, height is delta z. Now, what will be this side? We can easily figure out. Delta z square root over y delta y root over square, right? But we'll keep it a single value. We'll say this is delta s. Okay. Now, this fluid element will have weight. How will figure out the weight of the fluid element? It will always work downward, right? If it is a kind of brick, then half of the brick we are talking about, this half, right? So what is the volume of the whole brick? Volume of the whole brick is delta x, delta y, delta z. Now, if you like to get the weight, then you multiply by gamma, right? So if I make it weight, I have volume multiplied by gamma. But our full element is half of the brick. So weight will be, you need to divide by 2. That is the weight of the fluid working downward. Okay. Now, pressure force. Pressure always work perpendicular to the surface. So for this surface, for this vertical side, pressure working toward positive y direction. So I like to figure out that how much force working due to the pressure. We know pressure equal to F by A. So my force will be pressure into area. And similarly, and now what will be the area of this rectangular? Height is delta Z, and this arm is delta X. So this is my area, and this is the pressure. So pressure into area, that means force. This force working toward the right side. And now if you look in the bottom, pressure force working upward. And this pressure we are saying Py, and that means this one not the same. We are thinking along y axis, magnitude of pressure is Py, and along z axis, magnitude of pressure is Pz. Okay, so and this Pz working upward, perpendicular to the surface, into the surface, not the outward. Okay, so what will be the area of this rectangular? Obviously, delta x into delta y. So this is the area, and this is the pressure. You multiply, you get force working vertical direction. We'll apply the equilibrium equation of engineering mechanics, summation of fx, fy, or fz. Then we'll see how look like. Okay. Now, in the inclined surface, pressure also working perpendicular to the surface. This surface is inclined with angle theta. So inclined with horizontal axis theta, this angle will be theta. If you make a triangle, that means this angle is 90 degree, right? So this is theta, this will be also theta, the vertical axis. You can figure out easily. You make a horizontal line, this is theta, this will be theta, right? And this will be 90. And easily you can figure out this angle. I'm sorry, this is not theta. This will be theta. If this theta, this is theta, then this angle will be 90 minus theta. Then obviously this angle will be theta. You can figure out easily. Now, what is the area of this rectangular? Width is delta x, and length this side delta s. So delta s into delta x, this is the area into pressure. Pressure is PS. This much force working in this inclined surface. We are saying this is PS. Now we will apply the force balance. We apply this since this fluid element is not moving, so we can apply the summation of force along y-axis. We'll see what is happening. So along y-axis, we have one force right over here, working toward the right side. So right over here. And this force, we can make two components. One is horizontal, other one vertical downward. So horizontal one, negative y-axis. So PS into delta x, this is the force, and this is component will be sine theta, right? This will be cos theta, this will be sine theta. We'll apply sine theta over here. Now, in the triangle, you have, sorry, have to make it horizontal. This is delta y, and this height delta z, and this is theta, and this one delta s. So if you apply sine theta, this one I like to take out this delta z. So delta z equal to ds into sine theta. Right over delta z, or you can figure out sine theta equal to delta dz by ds. So this dz is substituted by this value. Now you see dx delta x will be out, sine theta will be out. So you are getting py equal to ps by applying force balance. Now we'll apply force balance along vertical direction. So along vertical direction, this is my pz, force working along positive z direction. So this is the force. Now you see vertical direction, we have three force. Number one, this one. Number two, weight of the body working downward. Again, this component of pressure force working in this surface. So total three force we need to take. So this one working vertical direction, and this one is the weight, negative because working downward. And this component will be cos theta, right? This term into cos theta. So this term into cos theta that we did. Now, ds into cos theta equal to dy right over here. If we apply cos theta in the triangle, you have this term becoming this one. Okay. Now, this value, delta s, del y, dz, they are very infinite small dimension. So we can think this value is very small and negligible. So we are thinking this is negligible, so this is come 0. So over here delta y will be out. So finally you are getting pz equal to ps. Right over here you got py equal to ps. So finally we are getting py equal to pz equal to ps. That means pressure, amount of pressure working in a point is same in all direction. Okay. And now what we are sacrificing here? And the weight of the fluid element we are neglecting. So we are not getting 100% accurate result, right? We are sacrificing the accuracy in our formula. How we will minimize that one? That's why we will do the experiment. You make some uh, design something based on fluid mechanics, then we test in the lab that what is the practical actual result is vary with the theoretical result. Okay. So this one in terms of static fluid. And this law, this is called fluid has same pressure in all direction. That is called Pascal law. Now, if you have a moving fluid, then what will happen? Then you cannot use this equation. Instead of moving fluid, a fluid is moving, then it might have different pressure in all three axes, three direction. So in that case, your pressure force will be average of 3, Px, Py, Pz divided by 3. Okay. Okay. Right. We already learned what is capillarity of the fluid, right? And if you take a very small diameter tube, you keeping in water, then you will see that water, your height of the water in the jar is this level. But water in the tube automatically getting up. That means you will see that this much height of the tube automatically filled by water. So this is called capillary rise. Now you need to figure out what will be the height of a certain fluid and how we can figure out that height and what it depends on which value. Number one thing that it depends on density of the fluid, then diameter of the tube, and also on surface tension. Now, our surface tension, what is the unit of surface tension? Force per unit length. That means Newton per meter. This is the unit of surface tension. Okay. So what we'll do, we'll make some force balance and try to figure out this value of H. Let's see how we can do it. Now, why this much amount of fluid? If I close this line and this line, you see, remain right, why is it not coming down? And obviously, it has a weight, this fluid, right? And you can figure out the weight. You figure out the volume of the fluid. If radius of this tube is r, diameter showing 2r, so what will be area of this tube right over here? So area will be pi r square. What will be the volume? You multiply by h. This is volume. So what will be weight then? You multiply by gamma. That means rho g. This is the weight of this amount of fluid. And this weight working downward. But fluid is not going downward. It is remain like that. What is the reason? So in terms of mechanics, that means somebody obviously pulling him up. Somebody is try to move downward due to the weight, but somebody pulling him up. That's why it is remains this static condition. If somebody pull him, more higher force, then this height will be increased. If weight is too much than the pulling force, then the h will be decreased. Now, you look carefully that if you look at the top surface right over here, this area, that means this mass fluid has a adhesion property more. They like to stick with the wall. Similarly, you look right over here. If I magnify right this region, then look like this one, right? That means this mass fluid like to stick with the tube. They have more adhesion property, right? So my question, why they are sticking over here? That means somebody is pulling along this direction and along this direction. And they have a certain angle. So I'm saying this angle is theta and this angle is theta. So this theta, this force surface tension, you can make two components, on horizontal, other on vertical. Similarly, this one on horizontal, on vertical. So how do you see? This horizontal force is opposite to each other, so it will cancel out. But this force working upward, how will going to balance? It will be balanced by weight of the fluid. Okay, that's why fluid will remain a little bit rise height of the fluid. Okay, so what we'll do, we'll make a force balance. So we figure out that this is the weight of this mass fluid. We already got it. Now I will see how much force working in the upward direction. So if you think upward is y-axis, we can say summation of force along y-axis has to be 0. So number one force working weight and working downward. So we can say minus pi r square is gamma. And obviously the tension force working upward, so that will be positive. And how much tension force working? Now you see sigma, what is the unit of sigma? It's a force per unit distance, Newton per meter. So this sigma vertical component will be sigma cos theta, right? Cos theta. You need Newton per meter. That means you need the distance. Now, how this surface force working? Is working if is through the all the periphery of the tube, right? Not only in the figure is showing you are looking from one side, but you think water rise throughout the periphery length of the tube. So what is the peripheral length? 2 pi r. So we can multiply with 2 pi r length, then you're getting the total force. So your force balance equation is coming right over here. And we know W equal to this mass. The W value is substitute over here. You just rearrange the equation, you'll get height of the fluid, H. Okay. Any question from here? Anyone, any question? No? Hello? Anyone? Are you there?
No, sir, no question.
No question? Okay. And now we'll solve a problem, okay, related to the capillary rise. Let's a very simple problem. It's saying you have to see the MathCAD file, right? You can see. Okay.
Yes, sir.
Yes, sir.
It's a 0.6 millimeter. It's a less than 1 millimeter. Very small tube, right? They inserted into water in a cup, and water temperature is 200 degrees Celsius. Determine the capillary rise of water in the tube. So a very fine tube, that means small tube, insert in the water, then you be able to see that water is rising, or this height over here you are getting. Okay, but my question that if you, this is our equation of the height, right? But you have water in your pot in home, and if you uh, take a plastic pipe, transparent, about 0.5 inch diameter, then see height is not increasing that much. What is the reason? Actually, theoretically, height will be increased, but you will not able to see, because you see right over here, if radius of the tube is increased, H will decrease. That means value of H will be very minimum. You will not able to see in your eye. But you decrease the radius, then you are able to, height will increase and you can see in your eye. Similarly, if density of the fluid, gamma value, is increased, fluid is more dense here, value of AC will be extremely low. Okay. And also depends on the this theta. If theta is 90 degree, then AC will be how much? 0. Cos 90 equal to 0. And if theta equal to 0, then AC will be maximum. Okay. So right over here it's saying that, and other thing you look carefully, that in this problem, your capillary, say I'm saying this is tube. Now, normally this is called curved surface, is called menicus, right? You remember, this is menicus. So right over here, what will be the direction of the surface force? Directly working in a certain angle. If you know this angle, you can figure out the component, vertical component and horizontal component. So this is theta. Now, if this theta is increasing too much, then maximum, what will the value theta? If fluid become straight right over, no rise, capillary rise. In that case, your theta will be 90. And you look, if theta is 90, then cos 90 equal to 0 in our formula, no height. And what's here, you're not seeing any height. But if theta is 0, then your cos 0 will be maximum value. Height will be maximum. So when theta might be 0, say this menicus making tangent, right over here is not making tangents about 45 degree, but if you make like that, or if I draw it right over here, or it making directly tangent at the wall, then right over here your sigma will work just parallel to the wall. In that case, your theta value will be 0. Okay. So after you insert the tube in the fluid, and if you look carefully, you are able to figure out the angle. Okay. So right over it's saying that shown in figure. In this figure is showing outside is air and inside is water. You need to figure out the capillary rise, how much height is uh, increasing. This value of H you need to figure out. So you have only one formula, right? And this data is given that is water temperature 0 degree. The mass will be surface tension 20 degree this mass. But what you are saying that 20 degree. So you have to take this is your value of your surface tension. Now, if you at first you leave what is given, you write down given diameter of the tube, convert in radius because you have the radius over here. And this is millimeter, then convert in meter. Surface tension in the from the table is given this mass. Okay. Rho is saying water. So you know the value of rho 1000. G value you know. And in that case, as per figure, angle phi or theta will be 0. So you just put 0 over here. Then you see capillary of rise equal to how much? Then you get the value. Coming in the meter, they convert in millimeter. So you see about 50 millimeter. Your thickness, diameter of the tube, 0.5 millimeter, very small, but water rising 50 millimeter, 5 centimeter, right? So you can easily observe. So any question from here? Let's go back to the, yes. Any question?
So do I have to take the theta value in radian or only the value?
Theta value.
Yes, sir. Is it in radian?
Theta value in degree. Theta value
Okay, sir.
in degree. Okay. And you see in this table, like kerosene is given 28 surface tension, soap solution, blood, then gasoline, glycerin, then automobile oil, AC30 oil, it has a surface tension 0.035. Then you have mercury. Mercury have the highest value of surface tension. Okay. So this sum table is given over here. I think this chapter is finished. Okay. So any question from this chapter, chapter 2? No question? Okay, no, then we'll jump on lecture 3. Okay. Let's just review this so far, how much we learned or how much we studied already last almost 2 weeks, right? So you see, we have studied what is the fluid mechanics, which law or principle you apply in the fluid mechanics, right? Then we talk about what is the application of fluid mechanics, why we are studying that, we talk about it, right? Then we learn about what is fluid and all the properties of the fluid, like density, viscosity, then specific gravity, we learn it, right? Then we learn different other property, like what is Newton law of viscosity, what is the shear force in a fluid, what is the behavior of Newtonian and non-Newtonian fluid. Then we learn what is bulk modulus of elasticity, what is capillarity, what is cohesion and adhesion. Based on those property, and we solve I think 2 problems, right? Then we study that what will be the pressure at a certain depth of fluid. Say you are designing a submarine and you like to know what will be the pressure at the roof of the submarine if submarine go underwater about 1 mile. So you don't need to put pressure gauge in the bottom of the sea, but you can calculate from your table that how much the pressure. So what happened if pressure on the roof of a submarine is too high? What will be the problem? Anyone? What will be problem?
স্যার ওয়াটার প্রেসারের কথা বলছেন?
Yeah,
স্যার ভেতরের প্রেসার থেকে ওয়াটার প্রেসার বেশি হলে স্যার ভেঙে যাবে।
collapse. It will
Yes,
collapse,
sir.
right? Same thing in human body. You are inside our body. How much pressure? Why
Same as
our
the
why blood is not coming out through our mouth, nose, and eye?
pressure balance due to
Pressure balance, because our inside our body has the same pressure. Pressure is atmospheric pressure, outside is atmospheric pressure, so it's balance. But sometime you might see in the news that if somebody went down in a well, Bangla, Kua, for cleaning, and they have nose bleeding and come out blood through eye, and they died because inside the well might be 30 feet deep. If you have a height of column of fluid, right? So pressure is high, and due to that high pressure, blood coming out through the body and people die. Same thing, if you are a like to swim in deep ocean, then you need to have tight suit, because in deep ocean you have pressure high, right? High pressure. So if you don't have anything, inside your body has pressure 14.7, but outside pressure might be 30 psi. So your body will be squeezed, your liquid from your body will be come out. The liquid is mainly blood. So that's why if you have a tight swimming suit, increase your body pressure inside, then you can go deep of the ocean. Okay. So why I'm talking that pressure is a very important thing. In fluid has a lot of property, because pressure is one thing, because from the pressure you are getting force. So if you a structure or a ship or a submarine or any other equipment, right, missile going through the fluid, right, passing through the air. So if you are not considering the pressure, your parcel will break down due to the pressure force. So you need to know that how you will measure the pressure. Say you are designing, you're working in a gas field, design pipeline from Kumilla to Dhaka. So you need to know how much will be the pressure inside and how will measure it. Okay. So next lesson or chapter will be based on pressure measurement, how we can measure the pressure, what type of equipment we use, and there will be some math that if you have used manometer, then how we can figure out the pressure. Okay. So let's share the screen. Once I might don't open, it seems like. Okay, now did you see the screen, right?
yes sir.
Okay, it's called pressure measurement. So let's go through the slide. Normally we use two type of device to measure the pressure. Number one thing is mechanical gauge. That means pressure gauge, some kind of meter, right? If you you have a car. In your car, you have the gas cylinder. You'll see in the gas cylinder they have a meter. It might be put at the front, but they have a meter to see the how much pressure is there. Then other thing we use the manometer, and we will explain it. What is the manometer? So in mechanical gas, you can just buy from the store and hook up with the pipeline or with your cylinder. You will get the pressure reading. But sometimes mechanical gas is not 100% accurate. If they are going to too old, then you will not get accurate result. For example, you will have blood pressure measuring device. Lot of device have electronic, you will see you can measure by yourself in home. But I see in US, I see in Bangladesh, some doctor use the electronic one. But in US, I see they never use the electronic one. But electronic one is available and it's cheaper. Most of the people buy it to check the blood pressure in the home. But when you visit the doctor, you'll see they are not using that one. They are using a wall-mounted pressure measuring device that they're taking reading from the mercury, how much you have the blood pressure. Okay, so liquid-based pressure measuring device is very accurate. Okay, now let's see what is the manometer. Okay, then we'll talk about the pressure gauge. Manometer is a device which measures pressure of fluid based on principle of balancing the column of liquid by the same or another column of liquid. And normally, what type of liquid will you use? Mercury, oil, alcohol, and water. Giving a example, say you have a pipeline and you have a leak over here, opening over here, opening over here. So through the opening, your fluid will came out, right? Fluid will came out, and right here fluid will came out. So where will be more loss? At the first one or second one? Anyone? Obviously at point one, leakage will be, water leakage will be more, because he's losing some water, then coming down, kinetic energy of fluid right over here is high, over here will be less due to the frictional loss. So our will be obviously at pressure 1, if I say P1 at point 2, P2, in that case, P1 will be higher than P2. Okay. Now, we are thinking a certain fluid passing through the pipeline. You can say, for example, natural gas. Now, through this tube, instead of keeping opening, you add a tube. Nothing. You put nothing in the tube. Here the tube. Then what will happen? Fluid will come through the tube, then flow along this direction, right? In the normal sense. Now, say is going here. If you going here, then you put some water in the tube. So say I'm putting some water, this much water. Now, how much the pressure over here? Right over here, he will try to push him down due to the pressure. right? You have water in the tube. Similarly, at point 2, right over here, if I say this is point 2, this is point 1, there will be some pressure. He also try to push him down, the water. And rest this portion will be filled up by the same fluid. Here is a air, there will be air. Now, if pressure at point 1 and point 2 is same, then what will be happen? There will be no difference of height. That means this height remains same, this height both on. Because pressure is same, both on is pressing the water by the same force. Or water is not go down. It cannot go down because it is inside the tube. But if pressure at point 1 is higher than P2, then he will try to push this water, and he also trying, but his force is less because pressure is P2 is less than P1. In that case, water height will increase right over here. So what is the difference between 2 point water height is this much. And by measuring the height, you can figure out the pressure difference between point 1 and 2. So that means what you are seeing over here, you are balancing a column of liquid by the another fluid or by the same fluid. So if a pressure device or pressure measuring equipment is based on this principle, then those device or equipment is called manometer. Okay, and we'll show you some picture that how you can measure the pressure with manometer and what type of manometer we normally use. There is a two type of manometer. Number one is called simple manometer, then other one is called differential manometer. Okay.
Sir, what is the meaning of column of liquid?
Column of liquid, uh, what it mean column? In the Excel, you see the column and row always horizontal, column always vertical. So column of fluid not mean the building column. That mean vertical, a vertical height of a fluid. Okay. You are swimming in a river. In the top surface of the river, you are swimming right over here, this level. Your depth will be this much. Then what will be the pressure on your body? P will be how much? P will be H, then rho, then G, H rho G, right? Because depth is H. Now, you are, say, just in your room, and you taking a tube of water, the height is same, and that one is on your body or on your head. Say this is your head. Now, this tube is full with water. Okay, so how much will be pressure? Just right over here, or top of your head. How much will be pressure? H rho G, same. Okay, because we always go vertical height of the fluid. So that means you consider a column of liquid working vertically, then you'll see what is the height of that column. That will be your pressure, and value will be H rho G. Always you need to think that way. Okay. Now we need to check that what is simple manometer, what is differential manometer. Simple manometer are used to measure pressure at a point, at a single point, or a single pipeline or a vessel, pressure vessel. That is called simple manometer. And most common time they use is called piezometer, U-tube manometer, single column manometer. We'll show you the, how look like the simple manometer and differential manometer. And right over here is differential manometer. Differential manometer, it measure the pressure between 2 points and give you the difference. That is called differential manometer. It's are used to measure the difference of pressure between any 2 points. And they are mainly, there is two piezometer type, differential manometer, inverted U-tube, then U-tube differential manometer, then they have micrometer. Okay, so let's see, we might have some picture of it or case. You look right over here, is left hand side is giving pressure at only one container. Say you have a big boiler or tank, and in this tank you attach a tube like L-shaped tube, and this is opening, and from this height H1 you are able to figure out the measure the pressure. Now tell me, say inside they have some pressure, and we add a tube, then what will happen? Why fluid is going, height is increasing? What is the reason? Anyone? Because you see, how much the pressure right over here? Atmospheric pressure, right? In the working in the top surface. What is trying to do? He tried to push him down. And pressure inside the container, they have some pressure. He will try to push him up. But if atmospheric pressure is too high, then what will happen? He will push him completely down. But this pressure is not that much high. So he tried to push the liquid upward. So from this height, you can figure out the pressure. What will be the magnitude? Pressure magnitude will be Pi inside the tank, that will be rho G H1, height of the column. Okay. Other thing, you look carefully over here, that if I make a line through this line, so how much pressure will be right over here, right over here? They will be different or they will be same? You need to response. Pressure will be same. Anyone?
So pressure will be same because of same height.
Good. Pressure will be same because you are in the same plane. So you see, by measuring rho H1G, you are getting actually pressure right over here. So right over here mean you are getting ultimately pressure of the inside the container. Okay. So this is example of simple manometer. This one also simple manometer, but this is U type. Okay. So right over here in the left side, they put the same fluid, right? Whatever the fluid is inside the tank, this is the same fluid in the tube. But if you have higher pressure in the inside the tank, then you can use E-tube type manometer. Say you have inside natural gas. So inside you can put mercury or other oil you can put. So in that case, you see right over here, atmospheric pressure, right, working, try to push him down, this fluid. And inside, they have a pressure, this tank. The pressure or through pressure force coming over here, he's trying to push him down. But inside the tank, pressure is high. That's why fluid is going upward. So what is the difference between these two height? If I make a straight line from this point, is H2, right? This H2 is the difference of height of the column. From that, measuring the H2, we are able to measure the pressure in the tank. And I make a straight line over here, right? What I'm saying, pressure right over here will be same, because they are making the same horizontal, passing through the same horizontal point. If I make one more line over here, then pressure right over here will be same. You make another line, same thing. Pressure along the line right over here and right over here will be same. Okay. And this one is E2 manometer. Normal this type manometer is available in the market. You can buy your home, your lab, or your reading room. Sometimes they have some electronic display. What is the humidity, what is the outside temperature, what is the density and pressure. Okay. And this one is differential manometer, because it giving pressure difference between 0.1 and 0.2. You see at P1 is higher than P2. That's why he is pushing him down along this direction, and this one going upward. Okay. Right. This one in the left side, this one is differential manometer, because it will give you the pressure difference between two tanks. And in the book, normally we give you the fundamental idea, but these two tanks might be, distance between them might be 300 feet or 200 feet, or might be 10 feet, or might be 2 meters. Depends on the what type of tank and where you are working, right? So you have one bigger tank over here, other tank over here. So from the manometry, you can figure out the pressure difference between two vessels. You see this one is pushing him down, and this one might be has low pressure. That's why fluid is going upward direction. And fluid right over here is different fluid. It has a property showing gamma 3. Fluid in the manometric tube, property gamma 2. And fluid in this tank A, property gamma 1. That means 3 type of fluid is used over here. Right side, you see on figure, the tube is inclined, but look like the same one. It will measure the pressure difference between two tanks. But why is the incline? Sometime you will see, you like to put manometer between two vessel, but there is not that much space, vertical direction. So you might have to put the tube in incline. And other thing, sometime is pressure difference is very low. Then from the vertical height, you cannot take the reading, because difference is coming very low. So in that case, if you incline the tube, then you will get the higher reading from the tube. That means easily you have to realize the how much fluid level is changing in the manometer. So that's why a lot of time they use inclined tube manometer. It depends on what type of fluid, where you are working, and depends also the space. Okay. Then mechanical pressure gauge. I think you might have seen those. uh, and mechanically available in the market. You can buy it if you want. Button tube pressure gas. This one, button tube. How it works? It is a tube right over here. The outside has a thread, but inside is a tube. So this one, if you put in your gas cylinder, then gas will flow through the tube due to the high pressure. And you see this carbon, this one also tube. So fluid will enter in the tube and it will try to expand. It is round. So due to the pressure, it will try to be straight. For this reason, this lever mechanism, this will try to move upward this direction. And finally, this movement will go through the lever and the pointer will get the reading. Okay. But why is the problem over here? You see, this pressure force is transmitted by too many mechanical parts. And if you use over the 5-year or 3-year, then you might not get the accurate result, because this tube work like a spring, right? Fluid entering, then it becomes straight. So gradually, on time, it become little bit flexible. Over the year, it will look the stiffness like you use a spring. You gradually do like that, do several times or 100 times, then the spring lose the stiffness. Same thing over here. Okay, but a lot of company, they use the very precise material, calculate correctly, then do the calibration, and they'll tell you that you buy this one, but you can use only 5 years. After 5 years, you need to buy another one. Okay. Then next one, diaphragm pressure gauge. You see diaphragm pressure gauge, how it works, that you have a pressure vessel. For example, this type. This is opening of the pressure vessel. Just give you an idea. Okay, you have opening. This opening, if you cover by some kind of membrane. Membrane mean some type of skin type, some rubber type material. Just for example, flexible. So due to the pressure, what will happen? This will bend little bit, right? Little bit. Now, if you attach something with this one, then he will try to move. So by this principle, the use is called diaphragm pressure gauge. So here is the diaphragm, and he see right over here. And due to the pressure, due to the moment of the diaphragm is going through this, this material, the vertical things. Then finally go through the pointer, and the reading. Then below pressure gauge, right over here, below pressure gauge, you see fluid, the high pressure entered through this hole. Then it flow around, coming over here. Then you see there is a folded portion right below. This will be folded, so it try to move upward. So that movement will pass through the lever and pointer, and you'll know how much pressure is there. And other one, right hand side, is called dead weight pressure gauge. How look like the dead weight? You see this one, this tube we attached with your pressure tank or gas cylinder, for example. And right over here, this is a piston, and there is a option you can put the weight. So fluid enter through the tube. Due to the high pressure, he will try to this piston move upward. How can keep him in the same position? You need to put some weight. Okay, that's why it is called dead weight pressure gauge. Okay. So far, any question? Anyone? No?
Sir.
Any question? No. Okay. how you can measure the atmospheric pressure. You have a mercury in a pot. In that mercury, you put a tube upside down. Then what will be happen? You will see due to the atmospheric pressure, the mercury will be go off and will fill up the tube. Because due to atmospheric pressure, he will push the mercury to flow the tube. But your tube has to be empty, vacuum tube. Okay. So traditionally, he used this tube to measure the atmospheric pressure. And how will measure it? So what he did, he put tube upside down and he was several days. And you see the height is increasing, right over here. So how much will be pressure over here? Over here will be same, right? Because the same horizontal line. So you can say pressure equal to rho g h, right? This is your atmospheric pressure. But after keeping some days, he realized that the height gradually falling down. What was the reason? Then he figured out that this mercury creates some vapor inside. And due to the vapor also try to, it has some pressure, he's trying to push him down too. That's why he observed that gradually it is going down. So what will be pressure over here? Height of column of this liquid plus this vapor pressure. So he got PV, that means this is atmospheric pressure, equal to gamma H, that means rho GH plus the vapor pressure in the tank. Okay. If you ignore the vapor pressure, then it will be only rho GH. Okay. Just give you an idea that how we can measure the atmospheric pressure and how column of height of the liquid can be sensed. Okay, you see a simple jar might be in your home. I like to measure the pressure at point A. Point A pressure will be same as this one. How can measure it? Anyone? How much will be pressure? At point A, pressure will be height of the column of liquid. How the height of the column? H1. So rho H1 G. But you look carefully, this is pressurized, so fluid like to go out. But from the top, what do we have? Atmospheric pressure. So pressure at point A will be rho GH1 plus this atmospheric pressure. This is at pressure at point A. How much will be pressure at point B? Same thing. Height how much? H2. So rho g H2 plus atmospheric pressure. Now, if I make a line along this line, and if I make several point over here, pressure will be same as point B because they are in the same level. Okay. Okay. You see right over here, kind of a E2 manometer. And inside the tube, they have different fluid. It's a rho manometer or say rho M. And this tank has some fluid, pressurized. And right over here, what we have? We have atmospheric pressure, right? So this atmospheric pressure working downward. And this fluid, due to the pressure, he is trying to push him down. That's why this fluid is increasing, height is increasing. Now, from here, how we can measure the pressure at point A? Okay. that we need to figure out. Okay, so how we can measure? You see, pressure at this point right over here. Let me take the other thing. This one. Pressure right over here, right over here, right over here, right over here will be same because they are on the same horizontal line. So any region, if we are able to measure the pressure at this point, you can say how much the pressure inside the tank. Okay. So you look carefully, this much height is given H2, this one is H1. And you can make a line, for example, over here. Then pressure right this point, right over here, and over here will be same because they are in the same line. Now, how much will be pressure at point B and point C? Has to be same or different? Anyone?
They will be different because two different type of fluid is used.
Okay, good. Actually, this will not be different. This will be same. But for example, I am taking 1 point over here, 1 point over here. In that case, the red one, pressure should not be same because these 2 points in the same height or same plane, but they are in different fluid. But in the bottom one, point B, I can say point B inside the black fluid. You can say it is also inside the white one, right? But for simplification, I will consider the point B, it remain inside the manometric fluid. So I will think pressure at point B and point C is the same. Okay. Now, I try to figure out pressure at point B from, I'll start from the tank A, how we can figure out. Okay. You see that at point B, what is the height of the column of fluid? H1, right? So I can say PB equal to H1 rho into G, right? But this one giving you only the pressure from this height, but is not giving you pressure, how much the pressure in the tank. So there will be, you need to add PA. This is the, you need to add PA. Similarly, because if it's opening, if there is a, what will you add? Say, I'm saying, for example, you have opening over here, nothing over here. Say tube is over here, and here is opening. Then how much will be pressure in over here? Atmosphere, right? Then you will say PB equal to H1 rho G plus P atmospheric pressure. But this is close. P atmospheric pressure, instead of P atmospheric pressure, we will say this is equal to PA. We don't know how much pressure inside the PA. It might be equal to the atmospheric pressure or might be higher than atmospheric pressure. But we will say this is PA. Okay. Now we will measure the pressure at point C. At points, when you measure the pressure at point C, I will not look to the left side. I always look to the right side. Okay. So you see, if what is the height of the column of fluid? H2, right? But atmospheric pressure is working right over here. So PC, if I say PC, this equal to, what is the height over here? H rho g, right? So I say H2 rho g plus P atmospheric pressure. Now, I can say PC equal to PB. If I say PC equal to PB, then I just equate the equation. On the left side, I have H2, then rho, then I have G plus P atmospheric pressure. And right side PB, PB H1 rho, then G, and in H2, this is the rho M, right? Rho manometric fluid, right? So rho G, then have P A. Now, is it possible to figure out PA from there? Easily, right? Is not possible? Because now you just simplify the equation. You can figure out the value of PA. Similarly, we did over here, AC. PB, pressure at P, we are saying PB equal to PC. Then PB equal to pressure at A plus pressure due to the height of the fluid. That becoming PA plus rho G H1. That we did right over here. PA plus rho on, H1 rho G. Similarly, pressure at point C is saying pressure at point D. What is pressure at point D? Is atmospheric pressure. So this is atmospheric pressure plus this height of the fluid. What is height of the fluid? H2. So is H2 rho manometric G H2. Then they say PB equal to PB. From there, figure out the PA. Now, you see, I like to figure out the pressure at point C. I start from here. PA plus this height. So when you are going down, okay, you are coming down, then it will be positive. You are coming down, okay? And the other way, you can figure out the pressure in PA. Instead of figure out the pressure at point B and at point C, how we can do? Let's see, you try to walk from point B, point D to point, you can walk through the tube coming at point A, right? You have one option. And your one more friend, he is very clever. So he's trying to walk this way. If I take a line, he pick up this way, he coming over here, then coming over here, then he stop. Who is smarter? Blue or red one?
Blue one.
Blue one, right? Because this extra distance is not making any sense. This one not making any sense because pressure right over here is the same. So what I'll do, I'll walk down from point D to all the way coming over here. Let's see how we can walk down. So what is the pressure at point D? P atmospheric pressure, right? Then you are coming down, right? So plus H2 rho G. So how are you coming now? At point C, right? That means you just walk down this mass. So at point C mean you are coming at point B. So I will say plus with this, hold on 1 second. This one, then I will say minus because I'm now moving upward, okay? Then that's why I will say minus. This minus, what is the distance? H1, right? Let me write down over here. Distance is H1. So H1 star rho into G. Now, where I came in, right over here, this point, right? This point. That means I coming in PA. So I say this equal to PA. And I look, you get the same thing. What is my PA equation over here? If you figure out the PA, right over here, PA equal to rho manometric GH2. That we get rho manometric. This is the manometric fluid H2. Then plus atmospheric pressure right over here. Plus atmospheric pressure. We have atmospheric pressure right over here. Then minus rho G H1. We have rho G H1 over here. Okay. So you have two options. At first, you look the problem, then figure out where you can take 2 points, where pressure is same. You cannot take right over here because pressure is not same. You cannot take it right over here. You are not passing through the same fluid, but you can take it over here cleverly because point B, I can consider it lie in the both fluid. Why I'm not taking in the bottom? Because there is no dimension. What is the meaning? Because if you take the at the bottom, then you need to walk down this much distance, then you need to walk up this much distance. Ultimately, no balance, zero. So why you will do the extra work, okay? Then you figure out pressure, those point, or you can start from one point, then walk down to other point, okay? Just remember, from the point is coming down positive. When you going up, pressure decreasing, okay? You are going bottom of the sea, pressure increasing, plus sign. From the bottom, you moving up, pressure will decrease, minus. That we apply. You see, we start from this point, right? Then walk down over here, and finally we are getting the same result. Similarly, you can start from point A, then go to the point D, then figure out that you are getting same equation or not. So far, any question? Any question?